Right before this tutorial, we implemented the constructor init method to define the object variables, and now we're about to define the act method for our agent to play an action given a certain state. And it will be very exciting because for the first time, we will implement a softmax policy to play the actions. All right, so let's do this. We're going to start with def here, and then we're going to call this function just like before, act, which will take as input first self for the object and then the state, of course. Alright, because the action that the agent will play at a certain time step depends on the state in which the agent is at this particular time step. Alright, then we're going to add colon, and here we go. Let's define this act method. So first, we're going to make sure that our state is in a batch. You know, we always need that extra dimension of the batch because very simply, this is what neural networks in PyTorch expect. And so, well, it's possible that we have some lost states not within a batch. So if that happens, we're going to make sure they are in a batch. And so with an if condition here, we're going to check if the dimension of our state, which we're going to get like that, state.enddim equals 3, because remember that the state is actually a 4-frame buffer, meaning a stack of 4 grayscale frames, and therefore you have one dimension corresponding to which frame it is among these 4 frames, and then the other 2 dimensions for the size of the images, 42 by 42. So if the dimension of the state is 3, meaning if the state is not in a batch, meaning if it is a single observation, meaning a single 4 grayscale frame buffer, well, what are we going to do? We're going to add this extra dimension of the batch by very simply not calling this time the unsqueeze method, because at this point the state is not yet a torch tensor, but we're going to do this super simply the following way by updating our state like that, by including it in a pair of square brackets, all right? And inside, of course, we enter state. So now we add this extra dimension of the batch, like in an extra pair of brackets in the NumPy array, and this makes sure that the state is now in a batch, okay? So now, if indeed the dimension of the state is 3, well, with this, what we do here, well, the dimension of the state will be 4, and therefore we'll have this extra dimension of the batch, which our neural network that we created here expects, all right? Perfect. So that's a good first thing done. And now that we have this extra dimension of the batch, well, time to convert the state into a torch tensor. And so that's exactly what we're going to do. We're going to take our state first, and we're going to update it the following way by first calling the torch library, from which we're going to call, of course, the tensor function, which will exactly convert our state right now in a NumPy array into a torch tensor. Okay, and well, this tensor function takes, of course, as input, well, the state right now in a NumPy array, but then, of course, as you can see, the D type, meaning the type of the values in the NumPy array, and then the tensor. And so, well, what is the D type? That's, of course, a float, right? Which we're going to note this way, torch.float32. There it is, perfect. And now, finally, we're also going to add the device, which we got here in the very first object variable of our constructor init method. And to do so, well, we're going to enter this last argument here, device, and this will be equal, of course, to our self.device object variable that we created before. So I'm pasting that here. And there we go. Now, not only we added this extra dimension of the batch, but also our state is a torch tensor. Perfect. And so, now that we have this extra dimension of the batch and plus a torch tensor, what can we do now? Well, since we have exactly what is required by our network here, we can simply call our network on the state to get the action values. And that's exactly what we're going to do. That's exactly our next step here. And so, well, we're going to create a new local variable, which we're going to call the action values. And we're going to call the forward method from our network object to get those action values. However, remember that the forward method in our network class actually also returns the state value, right? But right now at this point we don't need yet the state value. We will need it in the step method of the agent class. But therefore, since we're only gonna use the action values, well, what we're gonna do just below in this A3C class is add here a comma and then underscore, okay? So that we can disregard the state value, okay? And so now, well, time to first call our network, of course, self.network, okay? And then, as we just said, time to call the forward method. And then remember, in PyTorch, you have a choice. Either you can call the forward method, which takes as input the state from your network, or you can use the famous PyTorch shortcut by only calling the network. That's very famous. Whenever you implement the forward method in a PyTorch class, well, it knows that when you call your network like that, it's actually the forward method that you're calling. Okay, so as you want, let's keep the shortcut. And now, great, we have the action values. Perfect. So now, according to you, what is the next step? Well, by now I've mentioned the name many times. It's finally time to use softmax, right? We're going to use the softmax policy in order to select a certain action, right? Softmax is just another action selection strategy than the one we used before, epsilon greedy. So it's good that you know both techniques, and here it appears that softmax is better. So let's do this. We're going to create a new local variable which we're going to call policy, simply because we're about to use the softmax policy to select our actions. And now, well, time to use the softmax function, which we get from the functional module, which has a shortcut f, from which we indeed call the softmax function. Okay, perfect. And now, according to you, what do we need to input in this softmax function? Well, first, that's of course the action values, right? Because a softmax policy consists of converting our action values into probabilities. And then the higher probability, then the higher chance this action corresponding to this higher probability will be selected. And so there we go. We enter first here the action values, also called famously in reinforcement learning, the logits. Okay? So comma, and then we just have to add here dim, which is the dimension along which softmax will be computed, equals -1 to specify that the softmax should be applied across the last dimension, which is indeed the dimension representing the different actions. Alright, so let's do this. Let's add here dim equals -1, and there we go. Our softmax policy is ready. And so now we have one final thing to do, which is of course to return the selected action. And so we're going to add here return, and then we're going to use our softmax policy to sample the final action. And actually, right now it's important to understand that the state is actually a batch of states, but it's common practice to actually use this simplified notation, but let's not forget it's actually a batch of several states, and therefore what we're about to return now is several actions, each one corresponding to each state in the batch. And so since we're returning several actions, well, we're going to return them into a numpy array. So I'm calling the numpy library first, from which I'm calling the array function, and which will contain that list of actions for each state in the batch. Okay? So how are we going to do this? Well, we're going to use our policy tensor, of course, which again actually is a list of several policies for each of the states in the batch. And so what we're about to do in this pair of square brackets here is a for loop within a list, where we're going to loop over the different policies corresponding to each of the states in the batch. Okay, so let me show you. It will be easier to understand once we code it. So first, what I suggest we do is we do it for one policy, for one specific state in the batch, and then we'll do that for loop to do the same for the other states in the batch. Okay, so let's consider just one policy for now. It will be easier to visualize. And so now the question is, we're dealing with one specific state in the batch. How we're going to return that selected action? Well, we're going to use a certain function by the numpy library, more specifically by the random module from the numpy library. So here we go. We're going to call the numpy library first, which has the shortcut np, from which we call the random module, from which we call this choice function. The choice function which will allow us to draw from a certain distribution of probabilities, which is exactly what we have. Thanks to the softmax function here, we were able to get a distribution of probabilities over the different actions, the different action values for each state. And so, well, since we have this distribution, now we can use the choice function to sample an action from this distribution. And so, what do we have to input in this choice function? Well, first, the number of different actions we have for each state, and that's len of p, where p will actually be one of the policies in this list of policies for each of the states in the batch, and length of p here corresponds exactly to the number of actions. And then, as the second argument here, we're going to enter, well, the policy itself. And that's our argument here, p. We are going to enter p equals p. And p, of course, here will be one of the policies corresponding to one specific state in the batch in this policy tensor. And so, now in order to finish this, we simply have to add the for loop in order to loop over the different policies we have in this policy tensor. And so, what we're going to do, we're just going to add this for loop here. So I'm adding for p in, of course, our policy tensor here of the different policies for each of the states in the batch. Okay, so I'm adding policy here, but then we're just going to detach this policy tensor from the computational graph because we won't use any gradient to perform this computation of, sampling the actions from this distribution of probabilities. And so there we go. We're just going to add here dot detach, then parentheses. Then after that, we're going to add another dot and then CPU because we're actually going to send these sampling computations to the CPU. And then now that we detached the policy tensor from the computational graph, well, we're going to set this finally to a numpy array, which is why I'm adding to finish the numpy function. So that actually our policy tensor here is converted into a numpy array. All right. So basically, let's recap. Policy here started as a tensor, a torch tensor. Then we detached it from the computational graph. Then we moved the tensor back to the CPU. And then we converted that tensor into a numpy array. All right, so that these two formats here fit together and so that we can have the final actions in a numpy array. Perfect. So that's it. That's it for the act method. Now we have our actions returned for each state of the batch and following a softmax strategy. And so there we go. We are ready to move on to the next step, which will be to implement the step method, which will update our A3C model's parameters in each step of the training. Let's get some good energy for this one because it's actually going to be a long method to implement. So as soon as you're ready, join me in that next tutorial. And until then, enjoy AI. Step method. Indeed, that's the method that will be called whenever the agent takes a step in the environment, and it's a method that will receive the current state, the action taken, the reward received, the next state reached, and whether the episode is done or not, and which will update, of course, the model's parameters, meaning the weight of the neural network, so that it performs over the training better and better actions that lead to a higher score. Alright, so let's do this. Let's start by defining the step method that will take, as we just said, self for the object, but of course then first the state, then the action, then the reward, then the next state, and finally done. Okay, and once again, just to simplify the notations of the code, we are reasoning at the observation level, with a single state, a single action, a single reward, a single next state, and a single done. But in fact, what this step method will really take as input is a batch of states and then the corresponding batch of actions, rewards, next states, and dones. All right, but in order to avoid too many S's in the code, well, we're going to reason at the state level, but please keep in mind that these will actually be batches. All right, and now here we go. Let's implement that step method. Alright, well, speaking of batches, what will be our first step here? Well, this will be to get the batch size in a variable, because of course that will be one of the parameters we will need in all the upcoming computations. So here we go. Let's define a new local variable, which we're going to call batch size. And how will we get that batch size? Well, by simply taking our state here, which remember is actually the batch of states, and using the shape attribute, which we're going to access thanks to a dot here, and then shape, and then in square brackets, you're going to enter the index 0. Because indeed, the first dimension of the state tensor represents the number of state observations in the batch. Okay? Then, second step, let me actually scroll down so that it's easier for you. By the way, I put the zoom back so that we can all better see. And so now, what according to you is the next step? Well, at this point, when we actually call the step method, well, all these, the states, actions, rewards, next states, and dones are going to be numpy arrays, okay? And we want them to be torch tensors. So what we're about to do now in the next 4 lines of code is to convert the state, the next state, the reward, and done into torch tensors. And then we'll take care of the action later on. All right, so here we go. Let's start with the state. And well, you know how to convert that into a torch tensor. We first call the torch library, from which we call the tensor function, which will take as input, of course, the state currently as a numpy array. And then remember, we also have to add, just like what we did here, calling the tensor function. Well, let me remove this. Here we go. We have to specify the D type. Okay, so actually, let's be efficient because we already did it. Let's take this, let's copy this, and actually what we have to input here is, of course, exactly the same. All right, Perfect. So now we're going to do the same with, well, let's do our next states now because it's going to be almost the same. Right below, let's paste that and let's replace, of course, the state by next state, and here as well, the state by next state. Okay? Perfect. So now our states and our next states are converted into torch tensors, in their respective batch. And now let's take care of the rewards. So here we go. Let's do it efficiently again. I'm going to paste that same line of code. We're going to replace state here by reward. All right, there we go. Yes, reward, and then state here as well by reward again. All right, and then according to you, will we keep a torch.float32d type? Yes, of course, right? The reward is a float, and then we'll keep the same device, of course. So all good here with the reward. And now, finally, this is where things change a little bit. We're going to convert our NumPy array of the done booleans into a torch tensor again. So, well, let's paste that again. And here we're going to replace state by done. Okay, and then same here, state by done. Perfect. And now, what do we absolutely have to change? Well, of course, the D type, because done is not a float, it is a boolean. And so how can we get a boolean here? Well, very simply, we're going to replace torch.float32 by torch.bool. Okay, just like that. And that gives us indeed a boolean. However, now it's not over because we will use done in the computations and everything has to be in the same type. When we do operations of several elements together, well, we will still convert the done here into a float. And that's why I'm adding at the end here a dot, then 2, and then in parentheses, once again, D type equals torch float32. So let's actually take it here. It will be more efficient. Let's copy it and let's paste that exactly inside this 2. All right, and now we're all good. We only have floats here, so we can combine everything together in order to perform the future operations that will be needed for the A3C algorithm. Perfect, so now next step, well, time to finally take care of the action values and also the state value. All right, so let's actually get those at the same time because this is what returns exactly the forward method. So we're going to introduce new local variables here, which we're going to call action values. There we go. Then the state value. And how will we get those? Well, by calling, of course, our self.network object, which is our AI's brain, of course, which will take as input, of course, the state, which is actually a batch of states. Okay? And that's it. Next step done. And now, according to you, what do we also need to get in the same style? Well, we have the action values, we have the state value, but what do we also need for the future A3C computations we're about to implement? Well, actually, like in deep Q-learning, we also need the next state value. And so, here what we're going to do is call the network object again, but this time not on the state, but on the next state, because it will return to us the next state value. And it will also return the next action values, but we won't need them, and therefore we're going to start here with an underscore to disregard the next action values. However, we do need the next state value, and therefore I'm going to introduce a new local variable here, which I'm going to call next state underscore value. Perfect. And now, how do we get that next state value and that next action value disregarded? Well, by of course calling again our network, but this time on the next state. Perfect. So now we can move on to the next step, which is to compute the target state value by using the Bellman equation. So there we go. We're going to introduce a new variable here, which we're going to call the target state value, and which will be equal, well, we know this formula very well. It is equal to the reward plus our discount factor, or maybe you called it gamma. There it is, multiplied by, of course, our next state value we just got. Here it is, multiplied, of course, by 1 minus done. All right, the Bellman equation gets us the target state value. Perfect. And now that we have the target state value, what is the next step? Well, of course, now we're implementing the A3C model, and therefore the advantage feature comes into play. And well, that's exactly where we're about to get the advantage, because indeed the advantage is the target state value minus the state value. So here we go. Let's introduce a new local variable which we call advantage, and which is equal to the target state value minus the state value. Perfect. So now we have the advantage. And now let's get the other parts of the A3C model, which is, of course, the critic part. And well, that's also where the critic part comes into play, because now we're about to compute the total loss that will be back propagated into the neural network. And part of that total loss is the critic loss. Okay, so we're actually about to compute two losses, the actor's loss and the critic's loss. And that's also why we just computed the advantage, because the advantage is part of the actor's loss. Alright, so here we go. Our next step now will be to first compute the actor's loss, then we'll compute the critic's loss. But in order to compute the actor's loss, we need the entropy. And in order to compute the entropy, we need the distribution of probabilities over the action values and also the log probabilities over these same action values. So that's exactly what we're about to get now. We're going to start with the probabilities, which we're going to call probs. And of course, that's the same as the policy we got here. Only here, it's better to call it probs because it will be easier for us to understand the formula. But there we go. This is exactly the same. We're going to use the softmax function from the functional module applied to our action values across the last dimension. Okay, so I'm copying this because this is exactly, again, the probabilities we need right now. And now let's do the same for the log probabilities. And well, to do so, it's super simple. We're going to take this, copy it, paste it below. We're going to replace probs here by log probs. And here, instead of using the softmax function, we're going to use the log underscore softmax function. There it is, log softmax. Great, so now we have the probability distribution over the action values and the log probability distribution over the action values. So now that we have this, we can compute the entropy. And so there we go. Let's introduce a new local variable, which we call entropy, and which will be equal to minus the sum products of these probabilities and log probabilities. And so to get this, well, we're going to call the torch library first, from which we call the sum function, and inside we're going to put that product of the probabilities by the log probabilities. All right, so that's exactly what we're going to enter here. Probs multiplied by log probs. All right, so that's exactly a sum product here, log probs. And as a second argument, we just need to specify the axis dimension across which we do this sum product. And actually, this is still the last dimension. So I'm adding here axis equals -1. Perfect, so now we have the entropy. And so now we just need one final thing before we can get the actor's loss, which is actually the log probabilities of the actions that are actually selected. I'm talking about these actions here that are selected from this whole batch of states. And so how we're going to do this? Well, we're going to create an array of size, well, the batch size. And then we're going to use this array to select the log probabilities of the actions that are taken in the batch. Okay, so let's first create this array. We're going to call it batch underscore idx for index. And then to simply create this array, we're going to call numpy, which has a shortcut np. And then we're going to use the arrange function. And since the size of this array is supposed to be the same size as the batch, well, in this arrange function, we're going to enter the batch size, which is exactly why we had to get the batch size here. Okay, so batch size, perfect. And now, let me actually scroll down a bit. Now that we have this array of size batch size, well, we can use it to select the log probabilities of the actions actually played in this batch here, okay? And so, well, how are we going to do this? Well, first, let's call these log probabilities of the actions log p underscore actions. And then, how we're going to get them? Well, we're going to take our log probs tensor. So I'm going to take it here, log probs. And from this tensor, we're going to access, well, the indexes of the actions that are actually taken in the batch, which are exactly given by this variable action. Okay, but of course, we're going to take all the rows in this log probs tensor in order to get all the log probabilities for each of those actions selected. And in order to get all the rows, well, we need to enter first here for the first dimension, the batch idx, which we just got before, thanks to the arrange function by numpy. So batch idx here. And then, of course, for the second dimension, well, it's going to be only the indexes of the actions that are selected. And so here in the second dimension, I'm entering the actions. All right, the batch of actions corresponding to all the states in the batch. All right, amazing, because now we have everything we need to compute the actor's loss, because indeed, the actor's loss is going to be the negative mean of the product of the log probabilities of the actions taken and the advantages. And at the same time, we're going to encourage a bit of exploration by adding the mean of the entropy multiplied by a very small hyperparameter, which will balance the importance of the entropy. So let's write this. It will be simpler to visualize once we code it, but there we go. Let's introduce finally the actor's loss, which I'm going to call actor loss. And as we said, it is equal to the negative mean of the product of the log probabilities of the actions played and the advantages. So we're going to write this first. We take our log probabilities of the actions we just computed before. Here it is, log p actions, multiplied by the advantages. Okay, advantage. However, now we're just going to add to our advantage tensor a dot detach to prevent the gradients from flowing into the critic network during the actor's update, right? Because we won't need those gradients at this point. And then, there we go, we're going to take the mean of all that. And then, as we said, we're going to add at the end an exploration feature, which will be, as we said, the mean of the entropy multiplied by a very small number, which will balance the importance of this entropy. So here we go, this very small number is going to be 0.001, which we're going to multiply by indeed the mean of the entropy. And that's it, my friend, we have the actor's loss. Okay, that's exactly the actor's loss in the A3C algorithm. And now let's get the other loss, meaning the loss of the critic in the A3C model. And that's exactly what we're going to introduce now as a new local variable, which we're calling critic loss. And so what will be that critic loss? Well, very simply, it will be the mean squared error loss between the target state value and the state value. So here we go. We know how to do this. We take first our functional module f, from which we're going to call this MSC loss function, which we know very well. There it is, between the target state value and the state value. So let's enter first the target state value for the first argument. There it is. And then the state value. There it is again. And however, we're just going to detach the target state value from the computational graph because we want to prevent again the gradients from flowing into the target computations. Alright, perfect. So now basically we get the critic loss, which is the loss between the target state value and the predicted state value. And so now, super simple, what is the next step? It is obviously to get the total loss, which is simply the sum of the actor loss and the critic loss. So there we go. Let's introduce now the total loss, which is equal to the sum of the actor loss and the critic loss. Perfect. And so now you know the next steps, right? Because since we have the total loss, well, we can back propagate it into the A3C neural network and then use our optimizer to update the weights of that neural network. But first, remember what we always have to do before back propagating this loss and using that optimizer? Well, it is to reset the optimizer. Alright, so let's do that quickly. We first take our agent, which so far is self because we haven't created the A3C agent yet. We will do that in the next step, of course. So self, then from our agent we call our optimizer, of course. And then from our optimizer, since the optimizer is actually an instance of the Atom class and the Atom class contains this zero grad method that allows to reset the optimizer by zeroing out the gradients to prevent accumulation from the previous iterations. Well, there we go. We're going to use that zero grad method to zero out the gradients. Perfect. And now you know the next step. It is, of course, the back propagation. And the back propagation of what? Of course, of the total loss. So we're going to take our total loss now, and we're going to add this simple dot and then this simple backward function, which will perform exactly that backward propagation. And then, once again, you know the next step. Well, the next step is to finally update the model's parameters, meaning the neural network's weights, with our optimizer. So let's take again our agent, which so far is self because we haven't created the agent yet. Then let's take our optimizer again. And then let's take that other method of the Atom class, which is of course the step method, and which will exactly update the weights of the neural network to minimize that total loss. And now, my friends, well, it is time for me to say huge congratulations, actually double huge congrats, because let me actually zoom out now so that we can have a look at what we've just created. Because indeed, I want to say a first huge congrats for having implemented the step method, but also another huge congrats for having implemented the agent class. Indeed, we're done. We are done with the agent class. We have our 3 methods that we'll need to perform the training loop. And so there we go. Let's immediately run this cell to have this model architecture of our class so that in the next step we